All right, so the problem is the carts. All right, so the carts, let's say it only has three wheels, and I'm assuming it has an axle. And the axle is sort of an important thing because there's where you can really understand this effect. So this say this is your cart sitting on this wheel train, okay? And the point is that when you give this motion, part of the motion will be caught up in this rotation. So the mostly just the up and down movement, but you can sort of understand that there's motions in this wheel that are real momentum. That all of this matter is moving not only this way, but it has a bunch of other motions in it. Okay, so it's not only got this arrow going this way for the mass of the wheel and the mass of the axle, it's also got motions going up and motions going down. So it's got a lot of other directional angular momentum, and so it's storing energy. And so you can really understand if you think about the axle spinning, because it's just obvious that the hunk of metal is, it's going to have all these little atoms inside of it are going to be doing all of this rotating, and all of that is storing energy, and you won't see it in the motion this way. And the faster I spin that axle, the more energy it stores. So you can understand if the axle wasn't on the ground touching anything, I was just spinning it, you can understand that the faster I spin the mass, the more energy it would have. And I have to put it in with something. Something has to give it the energy. So all of this energy, the energy of the mass spinning, the energy it takes to spin the mass, all of that energy has to come out of your linear velocity. So you have to spin this, you have to reduce your linear velocity. So you'll be measuring a velocity, but part of that velocity, we do that in a different color, is part of your total energy is this part, the part rotating here inside the wheels. So the wheels contain a bunch of momentum that you can't see as a linear velocity. But if you bang it into something, all of this energy will be converted into forward pressure because that's the way it's actually moving, okay? Even though it's going up and down, because of the trap it's in, it can only give its energy, okay, as forward motion or pressure. So it will push, okay, as if it was a velocity forward when it's just a spinning velocity. It still has a pushing force forward. So you can collect it when you hit something. So the fact is when he throws the cart, the initial velocity is high, okay, and it's got a large percentage that's in the power of the wheels. And what he's doing is when he hits the second cart, he's converting or changing that relationship, because the other cart is going to be spinning the wheels less. So less of the energy is going to be in the wheels, and more of the energy is going to be in the linear motion. So the linear motion will be higher, and the wheel percentage will be lower. So I guess we could say it goes in, let's say this way, that percentage. And when it hits a heavier cart, he's going to get this. A higher percentage is going to be now in the linear motion, and a smaller percentage of the energy is going to be in the rotation of the wheels. And so that's why he can have the illusion of creating free momentum, because what he actually did was just change the ratio of how much energy was stored in the wheels and how much was in the actual linear motion. So they had the same momentum. It's just that one, you can't see it by looking at the linear velocity because it's hidden in the wheels. And in the second case, less of it's hidden in the wheels, so you see more of it in the linear velocity.
Okay, so basically what Gary is saying that when we have a one mass card, okay, and let's say, so the initial velocity is 100 meters per second in this direction, and so the momentum is 100, and it's going to collide into the two mass. And so theoretically, the outcome is that the two mass will have a velocity of 66 meters per second, and so momentum will be 133. And after reflection, card one will bounce back in opposite direction with velocity of minus 33 meters per second, and so the momentum will be 33, minus 33. So once again, of course, according to Gary, we have free momentum. So the initial momentum is 100, and after collision we have 133 this way and 33 this way, and so the total amount of free momentum is 66. So according to Gary, momentum is positive always, no matter in what direction. So 133 plus 33 equals 166. So we have 66 extra momentum, free momentum. And so now his explanation is that, well, actually, initially, we have, so 100 momentum linearly in this way, but actually we had also rotational momentum stored in the wheels. So we have the extra 66 momentum is actually stored in the wheels, the rotational momentum, and that should equal 66. So we had 100 of linear momentum in this direction, but we also had 66 rotational momentum that we couldn't see, but it actually was there to begin with. So the extra hidden 66 momentum is actually stored in the wheels as rotational momentum. So the total momentum of card 1 before collision is 100 momentum of 100 linear momentum plus 66 rotational momentum in the wheels. That equals to 106. So the total momentum now, according to draft science, is actually 166. So we have a linear momentum plus rotational momentum. And so now it makes sense. After collision, we have 133 this way and 33 this way. So what he says is light objects going faster. So yes, initially the one mass, so the light card went faster, all right, than the outcome. So light objects going fast well, at least light objects with on wheels, at least when they are resting on wheels, and they will have more rotational energy in them. Light objects going fast on wheels have more rotational energy on the wheels and on the axis, or on the axles. But now, what if we turn the scenario around? Instead of a one mass hitting a two mass hitting a one mass. So theoretically, once again, according to conventional science, when we have a two mass coming in with 100 momentum, with 100 meters per second, so the momentum is 200, colliding into a one mass. So after collision, the one mass theoretically will come out with 133 meters per second this way, so the momentum is 133. And after collision, card 1, the two mass will continue to move in the same direction, okay, like that, with 33 meters per second theoretically, and so the momentum will be 66. Now, so we have 200 initial momentum. After reflection, card 1 comes out with 133, and card 2 moves in the same direction with 66. When we add these two together, that already equals 200. This already equals 200. But now, if we apply this logic that faster objects, that the light object going faster also actually has rotational momentum in them, then this means, in this scenario, that this one, right, this one is coming out faster. The initial velocity is 100 meters per second, and it comes out with 133 meters per second. So it's a light object going faster. So it actually should possess also rotational momentum according to this logic. So it should possess a certain amount of rotational momentum. So this is the linear momentum, which is 133, but it should possess rotational momentum. I don't know how much, 20, 30, something. It should at least possess something according to this logic. So the total amount of momentum of this system here should be 133 plus a certain amount of rotational momentum. So this number should in fact be bigger than 133. But if that's the case, if this number is actually bigger, if the total momentum, so the linear momentum plus the rotational momentum, is bigger than 133, so let's say it's actually 150, then if we do 150 plus 66, that will equal a number bigger than the initial amount of momentum that went into the system. All right? So if this possesses rotational momentum, which it should according to this logic, this should possess rotational momentum because Gary says so, because light objects going faster possess more rotational momentum in the wheels. So this means that the total amount of momentum in this case should be bigger than this number. So it should be at least, 140, 150, 160, but then we also have to include card 1, the momentum of card 1 after reflection, 66. So this plus this, and that will equal a number bigger than the momentum that went into the system, bigger than the initial momentum. And so this means that this is going to be a free energy momentum, a free momentum experiment. Okay, do you understand this? Once again, according to draft science, light objects going faster possess more rotational momentum. So when we have a two mass hitting a one mass, and the initial momentum was 200, this one is coming out with 133, theoretically. And so that's going to be its linear momentum. But it also, in fact, there is some hidden rotational momentum in it. So, and let's say the rotational momentum is actually, 30. Or it could be 30. So now we have to do 30 plus 133. So the total momentum over here is actually 166. Okay, but now 166 plus 66. We should not forget this part here. Should not forget about this one. 166 plus 66 equals a number bigger than the initial 200. And so that's now free momentum. That should make sense. That doesn't make sense. These two are in conflict. The one mass hitting a two mass and the two mass hitting a one mass are in conflict according to the logic that the light objects going faster actually possess rotational momentum that you also have to include, that you have to add up with the linear momentum. Doesn't make sense. There is a conflict.